Right, so I'm going to be presenting some work on nuclear data uncertainty quantification in reactor physics parameters in Fluorine-19-based Molten Salt Reactor. And my name is Siegfried Stjernholm, that's the pronunciation. And I've been doing this work together with my supervisor Scholt Elter and also my subject reader Henrik Sjöstrand. So the table of contents for this talk is, I'm first going to explain why we should do these sorts of uncertainty quantifications, right? We need to motivate this work. Then I'm going to be talking about the role of fluorine-19 in reactor physics today and maybe also for the future. I will also be covering the methodology that I'm going to be using, the total Monte Carlo approach, the sampling of nuclear data, and then as well the molten salt reactor that we have at hand. Also, I will be covering the results, both from reactivity uncertainty and then also looking at individual reaction channels. And at the end, I will finish up with some conclusions and outlook. So this is just a figure to illustrate why we should do these sort of uncertainty quantifications. And we just heard some comments regarding this also in the previous talks. Let's say we have some quantity Q, or reactor quantity Q. We could take the fuel temperature, for example, in a solid fuel reactor. We have some sort of safety limit here in which we don't want to overcome. We don't want our fuel temperature to overcome the melting temperature of the fuel, for example. Then there are regulatory requirements, right? So the authorities, they will put limits on this temperature, for example, that you can't pass this because you want some sort of safety margin, right? And previously, back in the days, in the good old days, right, you did these sort of conservative calculations. So you did calculation where you assume the worst case scenario, and you did this calculations where you got the highest value, for example, for the temperature, the fuel temperature. But this gives quite a large estimate, and it doesn't leave a lot of room towards the safety limit and the regulatory requirements. So instead, what you can do is that you can do these sort of best estimate plus uncertainty calculations in which you calculate a mean value, and then you also calculate some sort of uncertainty such that you get a spread around probably around the real value, hopefully. And these calculations are often more precise, they more often reflect reality in a better way compared to conservative calculations. So this is a very good reason why you should do uncertainty quantification and not just conservative calculations. So looking at the role of fluorine-19 in reactor physics today, basically it's used in fuel enrichment as uranium hexafluoride for increasing the amount of uranium-235 in the fuel that we're going to use. So that's basically, it's used a lot in the fuel enrichment procedure, but not a lot in the actual core, in the fuel itself, once it's in the reactor. But there are potential future use cases for fluorine-19. So basically you have fluorine-based salts in molten salt reactors. That's one potential use case. So we had the molten salt reactor experiment in the 60s, which actually used fluoride lithium beryllium-based salt as a coolant and also as a solvent for the fuel. I think they used both uranium and also uranium-233 that came from thorium breeding as well. But there are also potential future use cases like fluorine-based uranium salts and fluorine-based thorium salts. So actually, it's quite important that we need to understand the nuclear data from fluorine-19. We need to understand the data and also especially its uncertainties that it brings. And this will yield us some information and where we need to do more work for like experimentalists and theoreticians. We have both present here in this room, so you will need to know where you need to work on. And also, we also get information on which level we can trust the simulations and criticality calculations, for example, when fluorine-19 is involved. So as for the methodology of this work, we use the total Monte Carlo procedure. So basically, it's used to quantify uncertainties in any general reactor quantity, Q, by performing some calculation several times with perturbed input data. And then you observe the spread in this Q, and we observe the spread in this Q as sigma obs. That's the observed uncertainty when you perturb the input data, run the reactor several times, and then you get the output. And in this work, we're also going to be we're going to be perturbing the cross-section from fluorine-19. That's the input data that we're perturbing, the nuclear data. And the contribution from this nuclear data uncertainty is denoted as sigma and d. So you might think that, okay, the sigma ND should be equal to the sigma obs, right? Because we're just perturbing the input data, so the uncertainty in the nuclear data in the reactor becomes the uncertainty in the quantity. But the thing is that we're going to be using Monte Carlo-based simulation calls, for example, OpenMC. And OpenMC comes with its inherent stochastic uncertainty, so we call this sigma stat. And then TMC method, it assumes that these variants can be split up, and you can just add them together. So the nuclear data uncertainty, or nuclear data variance, and the statistical inherent variance, can just add them up, and you would get this observed uncertainty. So we have this equation right here, the TMC equation. And okay, this figure is it's supposed to be colored, but as you can see here, the blue curve right here, this is just a K effective histogram, so it's just a histogram of 500 runs of the reactor. So the blue curve right here represents data that you get, the K effective data that you get if you run the reactor 500 times without perturbing the input data, just running it with different seeds in OpenMC, for example. And you get some sort of spread, right? But then, if you also perturb the input data, so not only having different seeds in OpenMC, you also perturb the input data, you get this broadening of the peak. So this is due to the nuclear data sampling then. So the orange width here is the observed uncertainty, and the blue width here is the statistical uncertainty from OpenMC. Okay, so how do we actually sample the data then? Well, in this work, we're going to be using Fluorine-19 cross-sections as input data that we're going to perturb, as I told you. And we will sample 500 ENDF files from Jeff 3.3 using a tool called Sandy and also Enjoy, which many of you probably are familiar with. But we're basically going to be using some modules in Enjoy that reconstructs resonances, broadens Doppler peaks, produces scattering cross-sections, and also, importantly, this last one, the error module, which considers covariance data in the ENDF file. So covariance data is saved in these ones for resonance parameters in 32, for cross-sections in 33, 34 is for angular distributions in the secondary angular distributions, and MS35 is the energy output, I believe. So energy distributions for secondary particles. And also you can, of course, sample individual reaction channels, which I will show you the results of later. Right. So this is just examples of what you get. Now these figures are also misfigured. You're supposed to see a distribution around here. I'm not sure why it's not showing up. Basically, there's a spread around here, the 100% and 50% percentile interval. And you can see here in these figures to the right the relative uncertainties. This is for elastic scattering of fluorine-19. So this is just an example. Again, this is neutron capture. It's supposed to show a spread in here, but also you see the relative uncertainties here. This is just an example of sample data that we get. Okay, so looking at the molten salt reactor at hand that we're actually going to be using for this simulation, these are just a top-down view and a side view. And I modeled this reactor model in OpenMC, so it's a Monte Carlo-based neutron transport code, and it's based on the transatomic power designs, open source and everything, so that's good. And we're going to be using a fluorine-based molten salt. So basically the green salt here is uranium lithium fluoride. It's a 5% enrichment. You have a zirconium hydride moderator and also a silicon carbide cladding. So these blue rods here, that's the moderator rods, and the green part is the molten salt. So that's the actual fuel. So it's kind of inverse of a light water reactor where the moderator is the fluid and then the fuel is the solid rods. So you have to think of it almost inversely. This is just for completeness, the composition of the fuel, moderator, and cladding. I will skip through that. And also some reactor quantities here, the temperatures. So we're just doing single physics, no multi-physics coupling. So we're using temperatures and densities and everything as boundary conditions for our problem. And of course, when you run this reactor, let's say you have it in operation and you're going to be running this, then the fissile fuel that you have is going to deplete, right? You're going to have a burn-up of your fuel. So what you need to do after a while, or what transatomic power wanted to do, is that you insert more moderating rods with time. So in the beginning of life, you would have almost no moderating rods inserted, but then once your fuel burns up, you would insert more moderating rods, and that would increase the thermalization, so you would get a more thermal spectrum, and that would increase the effectiveness of fission. So in order to compensate for the loss of reactivity, after a few weeks or months or whatever, you would insert moderating rods. So I've modeled 3 different reactors here, which I'll call thermal, semi-epithermal, and epithermal reactors. That's just 3 different stages of the hardness of the neutron spectrum. Okay, so going quickly through some results. Here we see the neutron flux as a function of the neutron energy, of course. And the orange plot right here is the epithermal system, which was the least moderated one. And the blue one is the thermal system, which was the most moderated one. And you see that the blue one is the least hard spectrum, it's the slowest spectrum, while the epithermal system is the fastest spectrum. And the semi-epithermal is kind of nudged in between there. So that makes sense. We're very happy that it actually looks good. And then we actually do this reactivity uncertainty estimations. So again, we used the Jeff 3.3, we did 500 samples using Enjoy and Sandy. And what you get is a uncertainty roughly of 60 ppm for the thermal and 200 ppm for the epithermal from fluoride-19 alone. So this is just sampling fluoride-19, no other nuclides and no geometrical sampling, just the cross sections. And the semi-epithermal is kind of in between here. So you see that the less moderated core, it has higher uncertainties due to fluoride-19. A possible reason for this might be that a larger fraction of the reactor volume is actually fluoride-19 when you have less moderated rods. You see here there's almost no green, but here there's a lot of green. So the green, that's the fluoride part, it will affect, of course, the uncertainties quite a lot more. It makes kind of sense. Another reason, as we saw in the samples I showed you with the spread that was missing, is the relative cross-section uncertainties are generally larger at larger energies. But of course, the relative uncertainties don't tell the whole story, because if the cross-section is super tiny and you have a relative uncertainty that is big, then it doesn't matter because the cross-section was so small, so it won't matter. So it doesn't really tell the whole story, but it might be a contributing factor. Right, so looking at the individual reaction channels, this table is kind of a lot to look at the first time. But basically on the rows, you have different reaction channels, elastic scattering, inelastic, neutron capture, all the other, some other reaction channels. And you see for the thermal and the epithermal system, I left out the semi-epithermal system, but you see the reactivity uncertainty contributions from different reaction channels. And also you can take the variance of that channel and divide by the total variance, and you see the relative contribution from that reaction channel. So for example, you can zoom out here and see for the thermal system, the main contributor is actually elastic scattering. As you see here, it's a kind of big piece of the pie. Also neutron capture here, alpha production here. So that's the thermal system. And then the epithermal system is elastic scattering, inelastic scattering, and alpha production. So that's the main contributors to this uncertainty. So we see that scattering actually plays a bigger role in the epithermal system, at least a relatively bigger role, piece of the pie. So one possible reason for this is that when you have less thermalization from the moderator rods in the epithermal case, then the role of fluoride-19 in thermalization is greater. It takes over the role of the moderator rods. So the uncertainties from scattering will, of course, be higher in that sense. Also, we saw that the relative cross-section uncertainties are larger at larger energies again. And we see this quite unexpected large contribution from this alpha production channel, this MT107, which almost contributes half of the uncertainty. So we were quite surprised by this, actually. But we also see in some presentation on Tuesday that work is being done on this reaction channel, so we're very happy about that. Right, so as for conclusions and outlook of this work, we saw that the uncertainties from fluoride-19 ranges from roughly 60 ppm to 200 ppm on that order of magnitude, depending on the level of moderation in the core, depending on the hardness of the system. And you also have that less moderating yields a higher uncertainty in the fluoride-19 data, which we saw. The epithermal system was the most uncertain system. And we also seen that other studies, actually from chloride-35, relating to the previous presentation also, that chloride-35 has shown a uncertainty of almost 1,500 ppm in the worst case scenario due to missing data, which previous studies have shown. So we need more data in these sort of reaction channels, otherwise we can have these large uncertainties due to just these small elements. And roughly half of the uncertainty comes from alpha production, so MT107, and we also need improvements in the evaluation for this and new experimental measurements and also coupling to theoretical models which is going to be done, thankfully, according to what we saw on Tuesday. And one thing we also observed was that JET 3.3 does not contain covariances for resonance peaks. It doesn't contain angular distribution covariances or energy distribution covariances. And we're kind of wondering how large this contribution would be. And also for other nuclear data libraries, for example, ENDF8, they don't also contain this data. So there's a lot of missing data for fluorine, which we're kind of surprised by because it's actually being used in the nuclear industry a lot, but there's so much missing data for fluorine. Also, one outlook from this work is that you should also, of course, investigate other reactor parameters, so not just K effective or reactivity. For example, power distribution. So we actually did power distribution and power peaking, but we saw that we used OpenMC for 2 group cross-sections at assembly level, and they gave kind of a rise to a large uncertainty just due to the calculations themselves and not actually due to the nuclear data. So it took a long time to compute. So we aimed at looking at this with deterministic methods instead, but there wasn't really time for that in the thesis. So yeah, thanks a lot for your attention.